And hello and welcome, ladies and gentlemen, to PASCO Laboratories, and happy Halloween! We're here live at PASCO Laboratories with Madame Curie. Welcome, Madame Curie.
Back from the dead just for a special appearance here today.
Thank you for joining us. To my direct right is Mr. Frank and Stein.
Aye.
And I'm JP. And of course, a lot of people always ask me, what does the P stand for? You guys know?
No.
It's a funny story, but the truth is the P stands for pumpkin.
Pumpkins.
Which is an odd middle name, I agree, but it's so perfect for this season in Halloween because we're going to be taking a look at pumpkins a little bit later and actually doing some fun stuff with them. Some fun living and dead stuff because it's all about living and dead today. The question is, what's alive and what's dead? And how do we know? Like, are these folks alive or dead? Am I alive or dead? Do you really know? Well, we're going to find out, and we're going to check some things out. So what's a great way to start figuring out if things are alive or dead? Madame Curie?
Well, if you're a human being, I think if you got a heartbeat, that pretty much settles it. You're alive or you're dead. They declare you dead when your heart is stopped, right? So let's check your heartbeat and see if it's beating, and do you have a pattern of all the valves and atria working together to get blood flowing through your body?
Okay, so that's one great way to determine if things are alive or dead is if there's a heartbeat. And of course, this will answer that question so many people here at PASCO have. JP, do you have a heart? And we're going to find out shortly, aren't we? So, all right, let's try it. Let's try it. Okay. We're going to test to see if I'm alive or dead, and if Frankenstein is alive or dead. You get to put in your choices right now. Do you think I'm alive? Why don't you just put it into the chat and let folks know. And what do you think about Frankenstein? Alive or dead? Well, we're going to find out. Madame Curie, guide me through this.
Okay, so we're going to hook up the EKG sensor to you on your left side. You've got the one electrode patch there. Put the red electrode from the EKG sensor to your left side.
Okay.
And that's going to be measuring the electric current, rather electricity, generated from the muscles pumping in your heart.
Okay.
On your left side, on the opposite, that green.
On my green side. I'm on the right side here.
On the right side,
on the right
opposite.
side,
And then the black is the wrist.
Okay,
Excellent.
so I've hooked things up with the wireless EKG. Just kidding. Just hook things up here, and now you're going to determine if I'm alive or dead. I'm going to relax here comfortably.
So the palms are up, relax, because this, again, any muscle movement it'll capture. So are you ready?
I'm ready.
Okay, and I'm going to collect some data, and we're going to look on the screen and see just a few seconds of data is enough. I'm already going to hit stop because I can see it, and I'm going to enlarge the data here. We've already got your data. You've got a heartbeat. Wow,
I do have a heartbeat at 82 beats per minute. My heart is actually really rapidly beating here.
That's a little high.
Which means I've got a lot of heart, but that's a good number, right?
Yeah,
so
it's okay.
The question is, am I alive or dead?
Well, this looks very much like you're alive. I can see very distinct PQ-RST waves in your EKG data here, and so the jury has come to a conclusion here that yes, you are alive.
I'm alive, and
you
I have a heart. Okay, now let's move this on over to Frankenstein. Frank, if I may, I'm going to put the black here, and I'm going to move the red over to here, and the green over to here. And you'll notice I've hooked him up the same way to the same device.
We'll set the sensor down and palms up.
Palms down.
Like that. If you can rest them on the table, I know you have to squat a little bit. There we go. Okay. All right, and we're collecting data.
And
I
am seeing
zero voltage on the heart trace.
0 beats per minute.
And also the heart rate is 0 beats per minute. There's no electrical activity here at all.
Interesting. And so it looks to me that Frankenstein is dead.
I think he's dead.
So on the alive or dead, looking at electrical activity, it appears that Frankenstein is dead and I was alive, and now we have some proof between the difference between alive and dead. But don't worry, Frankenstein, we have other things to look at that you might still prove out. Okay, so relax, we're going to be okay. Because EKG isn't the only way we determine if things are alive or dead. In fact, how about you and I play a little game? It's a little game called Dead or alive? You ready? I'm going to give you 3 things to choose from, and all you got to do is tell me which one of these things, or all of them, are alive. And what can you choose from? You can choose from dirt.
Dirt.
You can choose from a spider on its back.
Spider.
Or you can choose from a leaf.
Ooh, leaf.
Now, get your choice ready. Tell me which one of those are alive. Madam Curie, why don't you give me a hand with that? What are we going to do?
Sure, well, we can't use the EKG sensor on those things because they're not human beings. But we can get some evidence by looking with the microscope and zooming in. That's one way to look for life.
Okay.
We'll start with the dirt.
So we'll start with the dirt, and I'm going to come in here with my little microscope here.
Yep.
It's hooked into Spark View, and I'm able to look at this, and what do we see?
I don't see anything moving in there, but that doesn't necessarily rule out being alive. When we think of dirt, we think of non-living, inorganic, sometimes organic things, non-living mixed in there, but we're going to need some more evidence to really make a determination, but we'll come back to the dirt.
Okay.
So it does. I don't see anything.
I don't
any
see
evidence
anything
now.
alive, but so we're going to use that as part of our evidence. Now the next thing we want to take a look at, and I can pull this nice little microscope out of the little stand here and put it down. We've got a little spider down here, and I can zoom up on this. Ooh, that's a pretty good image. What do we see here, madam?
Well, you know, it looks very still. It maybe at one time was alive, but I'm going to guess that it's not alive right now.
Poor spider.
The
Yeah.
spider is looking dead. So
He looks
just
dead.
just from observation, I'm prepared to say that spider's probably dead.
I would agree.
I would have to assume that. And then the last thing we wanted to take a look at, I'll put the microscope back in its little holder here. I'll take away the dirt, and I'm going to bring up the leaf here. Very calm leaf. Let me adjust the microscope. Let's take a look. And what do we see?
Oh wow! Look, I can see that there's a vein there. Leaves do have a vascular system similar to human beings, right? Veins with
Okay.
things, different in plants and humans, nutrients flowing through them. in the plant.
So it could be alive, but
Could be.
again, I'm not saying there isn't anything conclusive here. Observation was nice, and it was good to have that as like the first step in detailing living or dead or alive. But it's not going to be the only way for me. I'm going to have to do something else.
Right, qualitative analysis is great, but let's add something quantitative. How about some carbon dioxide testing here?
Okay, and that's exactly what we're going to do. We're going to do some carbon dioxide testing. We're going to use the wireless carbon dioxide sensor. I've got my dirt, and I've got my leaf,
Okay, and
and I even have a light source to keep that leaf activated. So I have that ready, and I'm going to, actually, Frank, why don't you hold that light source on there? And I'm going to put my carbon dioxide sensors, I've got 2 of them, so I'm putting 1 carbon dioxide sensor in for the leaf, and I'm putting 1 carbon dioxide sensor in for the soil. And I am going to start a recording of these 2 items, and let's get that started, and let's see what it looks like. I'm capturing some data here.
nice. Wow, I can already see a trend there.
I'm actually seeing a rapid trend. In fact, if I didn't know better, I'd almost say these were mirror opposites. I'm seeing 1 carbon dioxide is rapidly decreasing, and 1 carbon dioxide is rapidly increasing. Which is which? What's going on here, madam?
Well, if that leaf is alive, that is the only thing in this room that can consume carbon dioxide through the process of photosynthesis. That is also why we have the light on it, because it's able to take its CO2 and recombine it into different molecules for its one way it does metabolism. Now that's what we see going on now because the light's on. But we've got the opposite going on in the dirt chamber. We looked at it under the microscope.
We didn't see
We
anything.
couldn't tell whether it was dead or alive. It was inconclusive, but now we see that CO2 is increasing, or was increasing when we were collecting data, and that would be indicative of some kind of living process, or maybe decomposition, or maybe a combination where
Sure,
carbon
living
dioxide is
organisms
released.
performing some type of activity within the dirt itself. And so
Right.
dirt being a big collective term of everything that's in there, we're recognizing that part of what's in there is something alive. And so to answer our questions, dead or alive, soil dirt, rather, is actually alive. And we saw it.
Yeah, so there's things in dirt that are alive. Dirt itself, the rocks, the inorganic, those are dead. So it's a mix of dead and alive in there.
Which is a great discussion of biotic and abiotic factors, isn't it? And then the leaf we saw was alive, and the spider we said was dead. I hope you got those correct. So if you're keeping track, dirt is alive, leaf is alive, Frank is dead, and so was the spider.
Dead.
But there's got to be an explanation behind why that carbon dioxide was being taken in by that plant. And so, Madam Curie, I know we're going to come back and visit with you soon. So I'm going to let you go because we're going to come back and visit your laboratory shortly.
Excellent.
And Frank, I need you to explain to me what's going on with this leaf and why did I see that number? Why did I see this with the carbon dioxide being absorbed? What was happening?
Well, we have leaf and light. Light makes the leaf produce energy from the light and produce molecules from the carbon dioxide in the air. It eats carbon dioxide and it makes bigger molecules. Those molecules go into something like the fruit of a plant or the wood of the tree.
Very elegantly said, Frank. I probably couldn't have said it any better myself. Who am I kidding? I could have said it a lot better myself. But I think your point is made that when you take a leaf and it takes in carbon dioxide, it makes things like this pumpkin. This pumpkin started off as carbon dioxide in the air and energy from the sun, and poof, I've got a pumpkin. Isn't that great? And so what would you like to do with this, Frank?
Pumpkin!
Yeah,
Smash!
no, I know.
No.
Yes, we probably would like to smash this pumpkin, but of course not inside. But we could take it outside.
Let's go outside.
Nolan's going to show us how. Nolan?
We here at PASCO pride ourselves with the science behind Halloween. And of course, if those of you who are mischievous like to take your pumpkins places, we've got a little ode to smashing pumpkins in 5, 4, 3, 2, 1.
Wow.
That's pretty cool.
That
That's
was
definitely very cool. And so that's a little game we like to call the pumpkin drop. And of course, what you were seeing here is the pumpkin being dropped off the roof and being dropped onto the force platform. And the force platform, of course, we're working within the specifications of the force platform and kind of knew up front what that was going to be. But a good guess for you at home, and you can type it in or you could shout out your answer. But what do you think the force was of that exploding pumpkin on the force platform? Do you think it was 10 newtons, 30 newtons, 100 newtons? Which one, roughly? 10, 30, or 100 newtons do you think for that pumpkin dropping and exploding on that force platform?
It was
Frank?
a 6-pound pumpkin.
It was a 6-pound pumpkin, and it was being dropped from a height of roughly 20 feet.
20 feet.
Okay. So, Frank, why don't you take us through and show me what it is that we're looking at here?
Well, let me open the data now that in the program that we have for Capstone, you can see as I've climbed on the roof and I have the pumpkin up at the top. And let's watch as the pumpkin lands on a force platform to measure that actual force. We're going to run this so you can see what that looks like in real time. It's going to fall down the length of that line where it's just a corner of a crack in the building or a seam in the building. And here we go. And it's going to be let go there.
Oh, nice. And so we instantly see, and I love the way that you have this synced up, Frank, rather, is that you've dropped that. We see the actual video analysis taking place. Conducting video analysis here, the pumpkin hits the force platform, and we see a spike. And if I'm looking at that number...
Almost 3,400, 3,326 or so newtons as that has extended itself onto the platform. Now, if we want to be able to measure the height and understand, what energy has been transferred into kinetic energy and then through momentum gets measured there, let's switch over to one where I've run the analysis. And we can run it slowly again. But what we can do is we'll take something we know the height of. That meter stick that you see that at the bottom, it's got large stripes. That's a 1 meter element. Actually, it's a half meter, sorry. That's 0.54 meters. No, that is 1 meter. That's what we use to set the distance on that film. And then we can measure the distance from the platform up to the top, which is 5.54 meters. So when I let that go, we're going to see that come down. I'm going to run this again. It should be a little slower. You can see the pumpkin coming down. And when it hits the forest platform, we have that peak that comes in, and I've got the tool measuring what that is. It's 3,300 newtons. That is 125 times the force of the weight alone after it's fallen 20 feet or 5.5 meters onto the forest platform.
Wow, that's great measurement. And so my apologies, I was off on our initial numbers. I should have said, is it 10,000, 30,000, or no, that's still not right. Was it 1,000? What's the number? 3,000.
It's 3,200.
3,300.
Yeah. I'm sorry, 3,300. You're correct.
So it's I was off by a factor of 100. So I hope you got the right number, even though I made the mistake. It's looking to me that impact force was about 3,300 newtons was that impact force on that scale. And of course, that pumpkin just exploded and went everywhere, and we were able to measure that. And we could do some pretty neat analysis with that. But what I love most, Frank, is that you're able to do some pretty good video analysis there and capture that data.
Absolutely. And if I were to turn this loose in the classroom to my little monsters at the time when I was in the classroom, I might ask a question about what's the force to cause that momentum from the top of the pumpkin till when it had smashed all the way down. And they could use these tools to measure that and the change in the momentum as it drops.
The impulse momentum that they could measure.
Absolutely.
And even capture that area under that curve to get the impulse.
Right.
Great stuff that we can do. Video analysis that helps me take a look at this pumpkin that was once alive, dropped it off the roof, and not so much, is it? So this is actually kind of some great stuff, but it's a little bit violent, Frank. And the fact of the matter is, with trick-or-treating coming up, I'm not necessarily sure I want any kids coming anywhere near you, or for that matter, Madame Curie, who also looked very dangerous. And of course, we're still in a time of social distancing, and so the question is there a way that we can have good trick-or-treating at an acceptable social distance? Do you think that's possible, Frank?
Madame Curie is smart. She has a good idea for Halloween. Let's go see.
Okay, all right. Let's do that. Let's go over to Madame Curie's lab. We're going trick-or-treating, Frank and I, to Madame Curie's lab. Let's go on over and visit. And here we are, Madame Curie's lab. Madame Curie. Oh, no.
Got a trick-or-treater.
Oh, trick-or-treat. And, whoa.
Oh, you ditch.
You have set up a very nice device here, Madame Curie, for doing trick-or-treating. What do we have here?
Well, what this shows is this is using two PASCO smart carts, a smart motor, a ballistic launcher with candy on the inside of the accessory. And we've used Blockly code to get the cart to move when a trick-or-treater crosses the path of that motion sensor. That triggers the cart to go forward, and then the code says launch that candy out when the cart gets a certain distance, and then reverse and come back so that I can reload it for the next kid. Right? So that will keep Frank and I at safe distance from kids. I can't give them radioactivity. Frank can't snap.
Can't be violent like Frank is, like he was with the pumpkin, and we're able to possibly catch that candy in the process. So we're going to give it a shot, okay, Madame Curie? Let's try it.
Okay.
Trick or treat.
Trick or treat come up to my front door.
Here we go, and here it comes, and oh.
And Frank can help you catch that one.
I am clearly not very good at this trick-or-treat thing, but I do have to admit that we're having a lot of fun doing it. Of course, this device is designed as a ballistic launcher that you can show how the laws of physics apply to things that are moving. I'm going to get it this time. And that's why we have insurance here at PASCO Laboratories, obviously. So a very neat opportunity to do some trick-or-treating. We are really very grateful. Thank you, Madame Curie. Where's Madame Curie? Back here, Madame Curie. Thank you so much for bringing this opportunity to our folks out there. And Frank and Stein, thank you so much. And of course, to all of you out there, we're wishing you the happiest of Halloweens, the best of luck, great teaching, and of course, good day.
Good day.
Happy Halloween.